Imagine a car that never shifts gears, no transmission, no clutch, no complex mechanical choreography happening beneath your feet, just smooth, uninterrupted acceleration. For over a century, the gearbox has been at the heart of the automobile, a masterpiece of mechanical engineering carefully designed to compensate for one fundamental limitation of the internal combustion engine. But what if that entire system was solving the wrong problem? What if engines were never meant to drive the wheels directly in the first place? And what if, quietly, a new architecture is emerging, one that could make the gearbox completely irrelevant? Today, we're going to understand why. To understand why the gearbox might disappear, it helps to understand why it existed in the first place. The internal combustion engine is not a flexible machine. It is, in many ways, a very stubborn one. It produces power efficiently only within a narrow range of speeds, what engineers call the optimal RPM band. Too slow, and it struggles to generate usable torque. Too fast, and friction, heat, and fuel consumption begin to spiral out of control. This creates a fundamental mismatch. Because the wheels of a car don't operate in a narrow range. They demand torque across an enormous spectrum, from crawling through traffic to cruising at highway speeds to sudden bursts of acceleration. And this is where the gearbox enters the story. The gearbox is not there to improve the engine. It exists to compensate for it. By constantly changing gear ratios, the transmission tries to keep the engine operating within its narrow efficiency window, while still delivering the wide range of speeds and torque that real-world driving requires. It is, in essence, a translator, a mechanical interpreter between two systems that speak completely different languages. Over the decades, this translator became more and more sophisticated. Manual transmissions gave drivers control, but required skill. Automatic transmissions removed that burden, but added complexity. Dual-clutch systems promised lightning-fast shifts. Continuously variable transmissions tried to eliminate shifting altogether. Each iteration, more refined, more complex, more precise. And yet, beneath all that innovation, the core problem never changed. The engine still had a narrow efficiency band, and the gearbox was still trying to stretch it across reality. This is where the story becomes interesting. Because what if the problem was never about improving the gearbox? What if the real issue was the assumption that the engine had to drive the wheels at all? In recent years, a different architecture has started to emerge. Quietly at first, almost overlooked. Instead of connecting the engine to the wheels through gears, shafts, and mechanical linkages, this new approach simply removes that connection entirely. The engine no longer drives the car. It generates electricity. That electricity is either sent directly to an electric motor or stored temporarily in a battery, and the motor, not the engine, becomes the sole source of motion. No shifting, no torque interruptions, no mechanical negotiation between mismatched systems, just energy, converted and delivered exactly when needed. This is known as the series hybrid architecture, and if it works the way its proponents claim, then the gearbox, one of the most iconic components in automotive history, might not just evolve, it might disappear. The limits of physics. At the heart of this story lies a quiet but unavoidable truth. The internal combustion engine is fundamentally constrained by physics. It burns fuel in controlled explosions. Tiny, rapid detonations happening thousands of times per minute. And while that process is powerful, it is also deeply inefficient. In most real-world conditions, a typical gasoline engine converts only about 25 to 30% of fuel energy into usable motion. The rest is lost as heat, vibration, and noise. But even more limiting is this. That efficiency is not constant. It peaks only within a very narrow operating window, typically at a specific combination of engine speed and load. Outside of that window, efficiency drops quickly. This creates a dilemma. Because driving is unpredictable, a car must handle low-speed crawling, sudden acceleration, steady cruising, uphill loads. Each scenario demands a different torque profile, a different engine behavior, but the engine itself cannot adapt efficiently across all of them. So instead of changing the engine, engineers built a system around it, the gearbox, the mechanical workaround. The gearbox is often celebrated as a triumph of engineering, and in many ways, it is. A modern transmission is a cathedral of gears, clutches, and synchronizers, precisely engineered to redirect power with minimal interruption. But its purpose is not elegance. It is compromise. Each gear ratio exists to artificially shift the engine's operating point, keeping it as close as possible to its efficiency peak. First gear provides torque multiplication. Higher gears reduce engine speed for efficiency. But every shift introduces disruption. A brief moment where power delivery is interrupted, where energy is lost, where mechanical components engage and disengage under load. Even the most advanced dual-clutch systems, capable of near-instant shifts, cannot eliminate this entirely. They can only minimize it. And then there is friction. Inside a transmission, multiple gears are constantly meshing. Bearings rotate. Fluid circulates. Each interaction consumes energy. Individually, these losses seem small, but collectively, they matter. In many vehicles, drivetrain losses, including the gearbox, can account for 10 to 15% of total energy loss. Energy that never reaches the wheels. Complexity, cost, and fragility. And then comes the hidden cost. A gearbox is not just inefficient, it is complex. Hundreds of moving parts, precision manufacturing, tight tolerances, all working together under heat, pressure, and continuous stress. This complexity leads to consequences. Weight, adding tens of kilograms to the vehicle. Maintenance, fluid changes, wear components, failure points. Cost, both in production and long-term ownership. And perhaps most importantly, reliability. Because every additional component is another potential point of failure. This is why transmission issues are among the most common and expensive problems in modern vehicles. And yet, despite all of this, the gearbox has survived. For over a century. Not because it is perfect, but because it was necessary, because without it, the engine simply could not function effectively in the real world. But now, that assumption is being challenged, because a new idea is emerging, one that doesn't try to fix the engine's limitations, but instead removes the need to work around them at all. And this is where everything changes. This is where the architecture flips, not evolves, not improves. It flips. Because instead of asking, how do we make the engine work better with the wheels? Engineers began asking a different question. What if the engine didn't drive the wheels at all? A different role for the engine. In a series hybrid system, the internal combustion engine is no longer part of the drivetrain in the traditional sense. It does not send torque to the wheels. It does not respond directly to throttle input. It does not need to accelerate, decelerate, or adapt to driving conditions. Instead, it does one thing, and it does it well. It generates electricity. Think of it less like an engine and more like a power plant. Small, controlled, optimized. Because once the engine is decoupled from the wheels, everything changes. It no longer needs to operate across a wide RPM range. It can run at a constant speed, precisely where it is most efficient. No compromises, no fluctuations, no wasted potential. The new architecture. So how does the car actually move? The answer lies in a completely different energy flow. Fuel is burned in the engine. The engine spins a generator. That generator produces electricity. That electricity either powers an electric motor directly or is stored temporarily in a battery. And then, the electric motor drives the wheels, not the engine, the motor, which introduces something fundamentally new. Electric motors don't need gearboxes. They produce maximum torque from 0 RPM. They operate efficiently across a wide speed range. They respond instantly. In other words, they solve the exact problem that the gearbox was designed to fix, but without the gearbox. Energy flow, from mechanical to electrical. This is where the system becomes fascinating, because at first glance, it seems inefficient. Energy is being converted multiple times, mechanical to electrical, to chemical, to electrical, to mechanical. Each step introduces losses. So why would anyone design a system like this? Because what is lost in conversion can be gained in optimization. The engine now operates at peak efficiency almost all the time. The motor delivers torque exactly when needed, with no delay. The battery acts as a buffer, smoothing out demand fluctuations, and most importantly, the system eliminates the need for mechanical compromise. No shifting, no mismatched torque curves, no inefficient operating zones, just controlled energy flow. Why this can be more efficient in the real world? In theory, fewer conversions should mean higher efficiency, but in practice, reality is messy. Traditional engines spend most of their time operating outside their optimal efficiency range. Stop-and-go traffic, urban driving, frequent acceleration and deceleration. All of this pulls the engine away from its ideal state. But a series hybrid doesn't care about driving conditions, because the engine is no longer reacting to the driver. It is operating independently, calm, stable, efficient. Meanwhile, the electric motor handles the chaos of real-world driving. Instant torque, regenerative braking, precise control. This separation of roles is what makes the system powerful. Mechanical simplicity versus electrical complexity. And then comes one of the most overlooked advantages, the removal of mechanical complexity. No multi-speed transmission, no clutch packs, no synchronizers, no gear sets constantly engaging and disengaging. Fewer moving parts, less wear, potentially lower long-term maintenance. But in exchange, the complexity doesn't disappear. It shifts into electronics, into software, into energy management systems. Because now, instead of managing gears, the system manages energy. When to generate, when to store, when to deploy, and how to do it all seamlessly. This is where the paradigm shifts. This is not just a new type of hybrid. It is a new philosophy. Instead of forcing mechanical systems to adapt to physics, it uses electrical systems to work with it. Instead of translating between mismatched components, it removes the mismatch entirely. And in doing so, it quietly eliminates the need for one of the most iconic components in automotive history, the gearbox. To understand how disruptive this architecture really is, it helps to see where it fits in the broader industry. Because today, the automotive world is not moving in one direction, it is splitting into three. On one side, there are companies like Toyota. For decades, they have refined the parallel hybrid system, where both the engine and electric motor can drive the wheels. It's a balanced approach, efficient, proven, scalable, but it still relies on mechanical complexity, still depends on power-splitting devices, still carries the legacy of the gearbox, even if disguised. On the other side, there is Tesla, a completely different philosophy. No engine, no fuel, no compromise, just batteries and electric motors. It's the cleanest solution, but it comes with its own challenges. Charging infrastructure, battery cost, range anxiety in certain markets. And then, there is this third path quietly emerging. Series hybrid systems, seen in technologies like range extenders, or systems such as Nissan's e-Power. They don't eliminate the engine, they redefine it. The engine becomes invisible to the driver, irrelevant to the driving experience. And this creates a strange possibility, a car that feels like an electric vehicle, but doesn't depend entirely on charging infrastructure. This is where the question becomes unavoidable. Is this just a transitional technology, or is it something more? Because if this architecture proves scalable, cost-effective, and efficient, then it doesn't just compete with existing systems. It rewrites the rules. And when the rules change, entire industries shift. Transmission manufacturers, supply chains built around mechanical systems, decades of engineering expertise, all suddenly less relevant. Less. Cinematic conclusion. For more than a century, the gearbox has been one of the defining symbols of the automobile, a mechanical masterpiece, a carefully orchestrated system of gears and ratios designed to make an imperfect engine usable in a complex world. It was never optional, it was necessary. But necessity is a product of limitation. And when the limitation changes, so does the solution. What we are witnessing today is not just the evolution of a component. It is the quiet disappearance of an entire philosophy, a shift away from mechanical adaptation toward energy orchestration, where engines no longer struggle to keep up with reality because they no longer have to, where motion is no longer dictated by explosions, but by electrons, and where complexity is no longer visible in metal, but hidden in code. So the question is no longer, how do we build a better gearbox? But rather, do we need one at all? Because the future of the automobile may not be about better machines. It may be about simpler ones. And in that future, gears might not just change, they might disappear.